pleasure today to listen to our new colleague, Dr. Sam Poppe, who is the visiting scholar, beneficent of the Polish grant, funded by NCN, National Council for Science, and NAVA, National Academic Exchange Agency. And he is the leader of the project you see on the screen. So please, you can start and tell a little about yourself and about your project.
All right, thank you very much, both people in the room and people somewhere in the cloud online, for attending today and coming to listen. I am Sam, and thanks again for allowing me time to speak. I did my PhD at the Geography Department in Vrije Universiteit Brussel, Vrije Universiteit Brussel in Belgium. I did a postdoc at Penn State, Fulbright and the IR scholarship, Penn State in the United States. Then I went back to Brussels, and now I am here. And today I'm going to take you on a little ride through my research that has led to the DeMo Planet project, which we started a bit over 2 months ago here at the Space Research Center. So DeMo Planet is a new project to simulate shallow magma placement in the fractured crust of Earth, the Moon, and Mars, like you see in our logo. I'm not doing this alone. This is an international collaboration with these people here at the bottom, but I will introduce them shortly after, and they will actually even appear in the room today. Thanks to the premiere of our hybrid technology, everything is possible. So, I'm actually a volcanologist. I've been studying volcanoes the past 10 years. And one of the big questions volcanologists have to answer is what happens before magma reaches the surface? Like, for example, here on the left side, in the Icelandic eruption at Fagradalsfjall, which started in May earlier this year, where after a period of earthquakes, suddenly magma appeared. And people were actually quite surprised by it, even Icelandic authorities, when the eruption really happened. Then another big surprise in September, the Cumbre Vieja eruption on La Palma. It's still ongoing. More than 6,000 or even already close to 10,000 people are evacuated, roads, houses destroyed, and this eruption is still going on. And volcanologists face this very difficult question to understand what happens with the magma before it reaches the surface and actually being able to forecast that. And imagine on Earth, we can measure earthquakes, we can measure gas output, we can measure ground deformation, all signals of magma arriving to the surface, but what with planets? We can actually only remotely observe those planets, like the Moon, for example. If you look at a nice bright night at the Moon, you see those dark fields. Those are actually lava fields. Those are remnants of ancient volcanism, more than 1 billion years old, on the Moon. And if we go then to Mars, for example, we find on Mars what we think up to now is the largest volcano in our solar system. Olympus Mons, that's the upper red arrow you see there. And there are some other volcanoes there, clear indicators volcanism happened. But there is also actually smaller features on both the Moon and Mars. On the Moon, we have 4 fractured craters. On Mars, we have uplifted domes that hint at some magma placement processes. And the project is all about understanding those. So if we zoom in on the Moon, this is a geological map from the USGS, and because the Moon doesn't have any atmosphere, any meteorite impacts its surface, and its surface is actually riddled by meteorite craters. Now, when a meteorite impacts a planetary body, it transfers energy and actually melts a part of the crust of that planetary crust. So you produce magma, and that then rises below those crater floors, as we think. And so on the Moon, we find some of those 4 fractured craters, where the floor of the crater is uplifted and fractured. as you see here on the right, on this elevation profile. And the question is really, what happens at the question mark? How do those magma intrusions look like in geometry and volume? How deep are they, etc.? On Mars, we have those uplifted domes. There are whole fields of those. Some uplift structures, even in this case here, in the Flegramontes area, you see this white dashed line. That's actually a vent where probably lava poured out at the surface. So we want to understand how this formed. And actually, we can come back to Earth and look at a very interesting case. In 2011, Cordoncoye volcano erupted in Chile, and it didn't produce any of those fluid lavas you saw in Iceland or La Palma area, but it actually produced a dome-shaped uplift with a lot of cracks, like you can see on the photo, and a vent on the side. And if you look at the elevation map, the blue to red map there, you have an uplift, the red area, and then a lava flow that exited from one of those vents. And we try to model what's going on there. Why? Because we want to understand what's the volume of the magma, the geometry, the depth at which the magma sits, etc. All very important information for volcano eruption forecast. And the most simplistic model would say, according to Castro et al., their publication Nature Publications, would say this could have been a laccolith. A laccolith is a magma body with a flat bottom and a domed roof, and the crust above it is bent elastically. And as a simple reminder, if we look at elastic versus plastic deformation, elastic, linear elasticity is the simplest way to represent deformation of a planet's crust. Think about the rubber band, you all have it in your kitchen. You stretch it, you release it, and it returns to its original position. So all deformation that is elastic is recoverable. We can remove the magma source and it's like nothing ever happened. Plastic deformation is non-recoverable. It's more complex. Think about pasta. You try to break it. Maybe it will bend a little bit, but eventually it will break. And it's pretty obvious with dry pasta that I won't be able to glue that back together. That's plastic deformation. And so elastic deformation is used in volcano forecasting methods, in numerical models, because it allows for simple mathematical solutions. Simple meaning fast. So we get volcano monitoring data and then we can fastly come up with a model, what we think the volume is, the depth, etc. of this intrusion. So as you see here on the left, we measure the formation of a volcano, plug the data goes into the numerical model, and then depending on the geometry of an intrusion, can either be a flat cryptodome, an inclined sheet, a vertical dike, as we call it, or a horizontal sill. And depending on those, the elastic model will come up with a different solution for what the surface deformation should look like. In the case of a dike, it's going to be what you could call a butterfly shape, but for a rather ball-shaped magma source or a horizontal sill, we get this dome-shaped uplifts that we also see on the Moon or on Mars. The question is that model actually correct? Because if we come back to Earth and we do geological observations, we see different things. This is an image from Oslo, from the Oslo Fjord, over the island, where as part of my PhD, we looked at some small scale magma intrusions. And what we see, and we see that in several other places on Earth, we see a very local scale control of fractures, different rock strengths of different layers that the magma intruded in, chemical interactions mainly between the magma and the host rock, the way the magma cools. All of these things really have an influence on the propagation mode and the deformation mode caused by the magma. In this case of Oslo, for example, we find opening mode fracturing and shear mode fracturing, which are respectively indicators of elastic or plastic deformation. So we find both in the same location, actually. And if we run numerical models, this is a paper that just came out earlier this week by Walker and colleagues, which I helped produce. We see that by just changing the shape of the tip of an intrusion in a numerical model, we can move from opening mode to shear mode deformation. So we can switch between deformation modes, even though we don't really change the radiology of the hosted intrusion. So all of this to say that there's enough indicators on Earth that magma emplacement processes are really complex. And we need to deal with that somehow, but the numerical and analytical tools that volcano observatories or even planetary geologists are using to understand the magma emplacement processes are right now rather using elastic deformation. And so we have to ask, are we doing things too simplistic now, and do we need more complex models? And to answer that question, we simply have to try. There is, however, another way, and that's laboratory experiments. This was a major part of my PhD, where we represent a planetary crust by analog materials. You can use gelatin, pigskin gelatin, which is a brittle elastic material. So more going towards those elastic analytical tools, but we can also use granular materials. And those are able to deform plastically, as we've shown during my PhD. So we scale that kilometers large volcano down into a sandbox that will fit on this table, 20 by 20 centimeters, and we inject pancake syrup in it, or golden syrup. You see a tube here of our favorite, Data Lyles, because it's nice and stable. It's a good analog for magma, natural magma. We place our sandbox in a medical CT scanner. Once you would hopefully not have to face soon, but would if you have a medical issue and you need to be imaged, you'll be going into a medical CT scanner. Well, we use the same. This is the CT scanner, a wide beam CT scanner at the University Hospital in Brussels, and it's specifically targeted to diagnosing strokes, because it can image a 16 centimeter section at once and do that repetitively over time. So we put our sandbox in it and continuously scan. So we get a whole time series of 3D images of our sandbox while that syrup intrudes. So we can actually really image the magma emplacement process as it goes on. And you can see me doing that here on the right side. But one thing we realized is that the materials we use, that sand and plaster, is not well characterized. So another major part of my PhD went into that. So silicate sand is a coarse-grained material, and it's quite weak. You can see that on the left side there. It makes a nice heap if you pour it out. On the right side, plaster is magnitude smaller in grain size, 10 microns, and we use that as a filler into the sand. And you can see here that plaster is stronger, it's able to support cliffs. Now, we characterize the whole range of mixtures of sand with plaster from 0% plaster to 100. And in this way, on this curve, we're able to reconstruct an increasing strength for those materials. So we can now really use different strengths of materials to represent different strengths of planetary crust, depending on the scale we want to look at. You might ask yourself, is this really representative for strong, competent planetary crust? Well, you have to bear in mind that we need to downscale our kilometers length scale from nature to the lab. So to represent stronger rocks in the field, we need way weaker materials in our laboratory experiment. And these data help us really scale. So we have this material well characterized, and what we can do in the CT scanner is we can use digital volume correlation, where we take subvolumes of our CT data and track them over time through our time series. In this way, we can calculate surface displacement in our experiment, like we can do at natural volcanoes, but we can also quantify the entire displacement within the entire volume. So how the syrup, analog magma, is really deforming the host material. And if we do that, I'm putting for a reminder here on the right side our example from Earth and our nice dough from Mars. And if we inject syrup into a quite big material, this is 20% plaster, then this is what happens. So this is surface displacement, and towards yellow is going higher. So you see a dome growing here above my magma intrusion. And finally, if that video will disappear, let's try that again. And stop in time. Right, you got it. So you get a dome and even an extrusion and eruption of syrup if you want. Compare that case with the case from Mars, and I hope you see that at least geometrically this looks quite similar. So we can use our laboratory experiments to really understand the emplacement process, which we can't on Mars because the volcanism is over here, and which we can't on Earth if we are looking at old, inactive volcanoes that are eroded and where we look into the plumbing system. On that cases, we only look at the final result with our experiments. We can do much more complex modeling than what we can do nowadays with numerical models. So we looked at the surface, but with our digital volume correlation, we can also look inside the scans and calculate displacement, the black arrows, and strains, the colors. And on the left side, you see a fatter dome creating more shear mode plastic deformation. On the right side, more opening mode deformation that moves towards elastic deformation, even though our sand cannot really simulate elastic deformation. So we can do all that with laboratory experiments, but there's actually right now not a complex model that can model plastic deformation during magma emplacement. And to really understand if the models used nowadays are accurate enough, and maybe that will be the answer at the end of this exercise, we need to try construct those complex models that are more realistic. So our DeMo Planet project, which stands for Modeling Magma-Induced Deformation on Planetary Bodies, tries to solve three main questions. First of all, looking at the field, how did laccoliths and sills deform the host rocks around them in the intrasphetic syncline in the south of Poland, I'll show you soon, floor fracture craters on the moon, as I showed, and dome uplift on Mars. The second question, magma is hot, so how does that thermochemical interaction between magma and host rock affect the emplacement process overall? And the third one, how can we now integrate all our observations from the field, our knowledge of planetary crustal rheology, the presence of fractures in a host rock, and those contact interactions, how we can integrate all of that into a new non-elastic formation model. So our aim is really to build a new modeling application. And I'm not doing that alone. DeMo Planet is really an effort, a collaborative effort. I am here at CBK, but there's also Daniel Meesch from the office in Wrocław, who is part of this project. And just this week, we have managed to hire another postdoc, which will join us in January to start working with us on the project. And we work together with Professor Mareka Blankiewicz from the University of Wrocław for the fieldwork in the south of Poland. We work together with Dr. Claire Harnett from UCD Dublin in Ireland for the modeling part. Professor Mike Heap from the University of Strasbourg will help running laboratory tests, rock samples. And then Professor Atle Rotewarten, Björn and Chris Eibert from the University of Bergen will help mapping fracture networks in our fieldwork in the south of Poland and integrating that into the numerical model. And this is our overall methodology. So we're first going to look in the first work package at our field and planetary examples, and then take rock samples from the south of Poland into the lab and extract strength properties, Young's modulus, tensile strength, etc. And then we're also going to look at those interactions, thermochemical interactions between the Earth, between magma, and the host rock in the field, and hopefully bring all of that information into a more realistic 2D discrete element method model. And the fifth work package we're doing right now, science communication. So rather than me going through everything, I invited each of the collaborators to send a short video that will explain their involvement in the project. And for the first, here is a picture from one of our field sites in the south of Poland. You have several quarries there, Kopalnia, on Milav. This is Permian trachyte andesite magmatic rock, and it's used to build roads, to build train networks. And they included into Permian layer sediments, sometimes volcanic ignimbrites. And here you see a case where the contact is right between the lower gray part and the upper purplish part, right here, where this whitish line runs. And those trachyte andesites are.
Our project will include a study of subvolcanic intrusions in the intrasudetic basin. It is a late Paleozoic intramontane trough which is located in Central Europe in southwest Poland. Geologically, it's the northeastern margin of the Bohemian Massif, which is a part of the Variscan orogenic belt. The intrasudetic basin formed broadly in a continent collision zone, especially in relation to orogenic processes such like late to post-orogenic extension and strike-slip tectonics. The Carboniferous to Permian basin fill is a volcanosedimentary succession made up of alluvial to lacustrine siliciclastic deposits with intercalations of trachyandesitic to rhyolitic lavas and tuffs and subvolcanic intrusions which are locally abundant. In terms of petrology, the volcanic rocks show quite evolved compositions. There are no basalts. Orogenic signatures are quite typical, but there is a gradation to within plate signatures. The primary magmas originated from subduction-modified mantle sources, but underwent significant extensive differentiation on the way to the surface. The intrasudetic basin is a synclinorial structure, fold-bonded, and it is approximately 60 kilometers long from northwest to the southeast. The basin fill is asymmetric. There are older and thicker deposits in the northwest, which become younger and thinner to the southeast. Volcanic rocks are relatively scarce in Carboniferous deposits, but within the Permian strata there is extensive complex of volcanic rocks extending across the basin. Volcanic activity in the basin culminated in the Permian times, and this climatic phase of volcanism included the deposition of widespread ignimbrite sheets across the basin, with related formation of caldera in the basin center, and followed by emplacement of trachyandesite laccoliths along the caldera margins, and the laccoliths will be the subject of our detailed study. The trachyandesite laccoliths and their country rocks, like mudstones, sandstones and rhyolitic tuffs, are well exposed in several extensive quarries. A good example is Świerki quarry, where the trachyandesites are nearly 100 meters thick. There are two laccoliths there separated by sedimentary rocks. The map's cross-section and photograph here show some more details. Another interesting locality is the trachyandesite quarry at Głuszyca. In places like Świerki or Głuszyca, we would like to study the contact zones between trachyandesites and their country rocks, with special attention to mechanical, thermal and chemical interactions between intruding magma and the country sedimentary rocks, to investigate the emplacement processes on magma in such settings. Thank you for attention.
Right, thank you, Marek. Most of these people are listening today online, so it must be ready to hear themselves speak. This is 2 weeks ago. You see myself on the left and Daniel Benish at one of the locations where we went on our first exploration to decide on the target zones for the rock sampling. So that is our field locations. We have these beautifully complex laccoliths in South Poland we can study. They are close by, no problem with travel restrictions, etc. So that's one risk in the project cancelled out nowadays. So we are going to try to understand what that contact between the magma and host rock look like. But if you look at that host rock there, that layered sedimentary body, the question is really, what are the strength properties of those rocks and how can we properly model them in a numerical model? And therefore we work with Mike Heap, whom we will bring some rock samples to analyze. And Mike is there to explain.
Hello, my name is Mike Heap and I'm from the University of Strasbourg in France, and I'm a collaborator on the DeMo Planet project. The main goal of the laboratory is to provide rock physical and mechanical properties for the large-scale numerical modeling. The key properties are uniaxial compressive strength, Young's modulus, and tensile strength. However, the laboratory is well equipped, and if needed, we can provide a wide range of different rock physical and mechanical properties. Here's an example of the equipment that we will use as part of the project. This is a uniaxial load frame, and this can provide uniaxial compressive and tensile strength of rock materials, and the resultant mechanical data can be then used to determine elastic constants such as Young's modulus. However, values from the laboratory cannot be used directly in large-scale modeling, and they require an upscaling before they can be used. And this is because the laboratory values do not take into account large-scale features such as fractures. However, we are well experienced in Strasbourg at upscaling these properties, and this is what we will do for the project. Thanks for your attention.
Right, thank you, Mike. So we're going to take small rock samples into the lab, as Mike explained, and get strength properties out of them. But as Mike touched on, one of the very well-known problems is we then know the strength of such a small block of intact rock. How does that scale up to an entire rock pile that is riddled with fractures, faults on volcanoes themselves? We have lots of fractures, planetary crust like Mars. Think about the geological history that crust went through with volcanism, dike injection, etc., or on the moon, continuous impact of meteorites at times. So we need to somehow upscale those strength values. And one way to do that is by extracting fracture networks, which we can observe in field sites, and then translate those values into virtual fracture networks that go into the numerical model. And for that, we're working together with the team from University of Bergen, where we'll be using drones and photogrammetry in the field. And Björn Nyberg is here to explain this.
Hi, my name is Björn Nyberg, and today I'll be talking about virtual outcrop models and fracture network characterization that we do here at the University of Bergen, along with my colleagues Atle Rotevatn and Christian Haug Eide. So we use the virtual outcrop models to map faults and fractures, to understand how they interact and influence each other at different scales, and how that influences both the local and regional geology. And certainly there are a variety of ways to create the virtual outcrop models and different workflows. But typically the two main methods are either the use of a LiDAR to create a detailed point cloud mesh and making a triangularization of that to create a 3D model, or what's become more popular as of recent is the use of drones and photogrammetry to take a series of pictures of a cliff section, creating mosaic of those different images, and using the angles at which that image was taken to create that 3D model. Now, to visualize this, What we typically use is a software called Lime, which is developed by the Virtual Outcrop Geology Group at Norse here in Bergen. And this is just one example of a Carboniferous Permian fracture joint network. And if you're interested in viewing this model in more detail, you can go to this URL right here. But this model is in Cornwall in the UK. But the nice thing about Lime is you can view the virtual outcrop seamlessly at different scales, but also start to make interpretations. So what you see here in the blue lines here are interpretations of different joints in this virtual outcrop then. And you can create more and delete them and edit them, etc. What we can also start to do is take this 2.5 dimensional interpretations and project it onto a 2D plane. And what's nice about projecting onto a 2D plane is now we can start to make some more statistical analyses about the interactions of some of these fractures. And to do that, we take this image here, or this 2D plane, into a software called Network GT. And Network GT is an open source software that we have built to digitize, sample, and analyze the geometry and topology of 2D fracture networks. So when I'm talking about geometry, I'm talking about measurable things. So for example, the length, or the orientation, or the distribution of lengths in a fracture network. Essentially, elements that you can measure in units and dimensions. Whereas topology is the relationship of those fractures and how they are connected with one another. So by having knowledge about the geometry and topology, we can start to understand the fluid flow behavior across that fracture network. And that's what we see in this video here, where we see the 2D water phase fluid flow from left to right. So again, all of these sources and tools that I've been talking about here are open source. So if you are interested in any of these tools, just visit this URL. And if you have any additional questions, please do not hesitate to ask. Thank you.
All right, so Bjorn just wrapped up what we're going to do in the field here in Poland. But then, of course, as I showed before, we're going to study in detail those floor fracture craters on the moon and uplifted domes on Mars to try to constrain surface deformation patterns as another input or comparison for our models, for our numerical models. And now, the real bulk, the center of the project, the numerical model. So we're going to try to build a new application of magma emplacement in a distinct or discrete element method model, a DEM model. And what this is actually pilot balls that acts as an analog for planetary thrust. And we are going to inject another stream of balls that is given interactions or contacts between those balls, or actually in this case spheres, because we are working with a 2D model at first. And this stream of balls will act like high viscosity magma, like the one we think created the trachyte andesites in the south of Poland. And we are also going to feed into it discrete fracture networks and our field observations of rock strength. But here to explain more about the DEM method is someone who's been working with this for several years, and that is...
Hi everyone. So I'm Dr. Claire Harnett from University College Dublin in Ireland, and I look at using discrete element modelling in different volcanic tectonic scenarios. So to give you a bit of background, the discrete element method, or DEM, is a modelling method by which you use rigid spherical particles or circular particles to discretize a material. And the way in which you control the material behavior is by looking at the contacts that exist between these particles. So you can see these in red and blue in the kind of schematics, and these contacts are defined by their normal and shear stiffnesses. And you can see very simply, if we reduce the angle of friction on one side of our kind of pile, then we can cause a mechanical material failure. And the discrete element method is really good for modelling large strain processes, and we can also use some kind of post-processing to look at the strain that develops in the subsurface. So this makes it really applicable to a lot of scenarios. One scenario in particular that I've spent a lot of time looking at is lava dome extrusion. So you can see here we have a red material in the core, which is behaving as a fluid, grey material around the outside, which is behaving as a solid, and you can see how I'm simulating dome extrusion by adding material through the conduit. And the really nice thing here is that you're getting kind of this dynamic rock falling as the dome is growing, and this is one of the reasons that DEM is really well placed to model something that has kind of dynamic strain accumulation throughout the process. This is some work I'm doing at the moment looking at caldera collapse and slope formation. So what we have here is a piston, that's kind of the white space at the bottom in the middle, that is moving downwards, and we're looking at how the material forms slopes as that piston withdraws. So what kind of slope angles do we get? How does the material behavior affect those slope angles? And the kind of blue lines you're seeing here are the contact forces. So how does the local force change as we withdraw and remove material? So I'll be helping to advise on how we can use DEM in the Demo Planet project, and I'm looking forward to get going. So thanks very much.
So as you saw for a second, Claire was supposed to show up in the top right corner, but somehow her video decided to hide behind the black box. But I'm really thankful for all those bright minds to assist in our main goal of building this new numerical application. And so as a summary, I can't give you results yet. We'll be back in 2 years and see how it all went. But we really hope to provide a detailed geological study of the emplacement of those trachyte macroids in the intraspheeric synclinorium in the south of Poland. And then use the information we learned there to build that new discontinuum medium, that DEM model, to simulate magma emplacement in fractured planetary crusts. To answer those two questions, to integrate everything into that model. And so hopefully within 2 years, we'll be back with first results of our new modeling application. And we hope in the further future, this can then be used to validate, to benchmark elastic numerical tools that are used to understand volcanic activity on Earth and other planets. And of course, if you have more questions, I'm obviously open to questions now from the audience physically here or somewhere in the cloud. If not, please get in touch. More information or updates about the project will appear on my Twitter feed at Sam Poppe. As you saw before, most of the contributors, collaborators are also on Twitter. So reach out or use my email. And of course, please do visit my website to learn more about my background. Thank you very much.
Thank you.